Hello and welcome back to the channel. Today we're talking about TextGrad. TextGrad is a Python package that does automatic differentiation via text. And that basically means that if you have an application where you're using some kind of an LLM to do prompt engineering, you can use TextGrad to optimize your prompt. And it's not just optimizing your prompt, as we're going to see in this video, through a series of 5 examples where we are going to be optimizing code, optimize equations, solutions, and we are going to even use a dataset to tune our prompts. They also have a paper which sort of goes through the under the hood stuff about what's actually happening here. So if you look at this paper, they compare the text gradients with the numerical gradients that we obtain through backpropagation when we're training a neural network. If you're not familiar with neural networks, you start with some input, you pass the input through a series of network layers and you receive your final output, and then you calculate the loss. The loss basically means how different your prediction is from your desired output. And then you use that loss to compute the partial derivatives with each of these weights to update the weights in the network via an algorithm called backpropagation to minimize the loss of the output and the target. Similarly, they use natural language gradients to do backpropagation through an LLM system. For example, suppose you have some sort of a system which inputs a prompt, some sort of a user query, some other inputs, and then it passes the prompt and the query through an LLM to receive some output, and then does another LLM call to find the final output. What you can do is use some sort of an evaluation instruction and pass the final output and that instruction into a different LLM that's going to calculate your loss. This second LLM here is just going to compare the final output and the evaluation instruction and basically output text that gives feedback to the LLMs that came before it. And so we are going to be updating the LLMs from here and here by providing the feedback we obtained from this loss, and then finally update everything until we update the prompt again. As we go into the tutorial section of this video, I think hopefully everything will start to become more and more clear. Also, do check out my video on DSPy, which is another prompting framework, and I have a video on that with 8 examples that runs you through the entire DSPy framework. The main difference between DSPy and TextGrad is that DSPy really allows you to stop prompting altogether. It creates this modularized approach to creating LLM applications, and I think it's very powerful at that. TextGrad, on the other hand, is more about optimizing prompts, optimizing solutions, optimizing queries, and it's not trying to eradicate prompt engineering altogether. Both TextGrad and DSPy are pretty impressive libraries, which I think are going to be really useful and really big in the future. So it's very important to learn these libraries now as they're getting started, and these libraries are going to keep improving as time goes on. So let's start with a very simple example. Suppose I have this sort of a question string. Question string here has a question that we are going to be asking to an LLM, specifically this GPT 3.5 turbo model. So the question string here says, if 10 people got new jobs in March, 15 people got jobs in April, how many people will get jobs in May? Answer a number or say, answer, I'm very bad at this if you can't determine the answer. Obviously, the answer to this question is that the answer cannot be found because the number of people who get jobs in May has absolutely no correlation with whatever happened in March and April. But can we make the LLM say that? And actually, it has to say, I'm very bad at this. Let's see what the model answers if we run this. And here you can see that we are passing the question into the model. The model is this black box LLM object that we have defined here with this GPT 3.5 turbo module. So now if we run this, the answer it gives is 20. So the LLM thinks that, okay, 10 people got jobs in March, 15 got in April, so obviously 20 people are going to get jobs in May. Obviously that logic is very flawed. But how can we make this text gradient idea inform the LLM that your idea is flawed? Let's see how to do that. Well, first of all, we are going to create this optimizer called the text gradient optimizer. So we have this thing called TGD, which is basically, as you can see, is a text gradient descent optimizer. So it's kind of analogous to how we have the SGD or the stochastic gradient descent optimizer in things like PyTorch or TensorFlow. So it's basically going to help you reduce your loss after you calculate the loss. And here we provide what we want to optimize. So in our case, we are trying to optimize the answer. And if you remember, answer is basically the thing you get back when you pass your question through the model. So if you kind of go back to that diagram that we saw earlier, we have some sort of LLM pipeline, and then we have this evaluation instruction that looks at the final output to output a loss. So that's what this evaluation instruction is going to do. So we're going to provide it the question string, which is basically that question that we wrote out, and we're going to ask it to evaluate the answer and give concise feedback on how to improve it. And now we run this function by using this tg.textLoss, which basically is going to be a class that evaluates a response. If we run this and then look at the loss value, which is basically the loss value is what the evaluation model told us about the question. It says that the answer 20 is not logically determined based on the information provided. The question does not give a clear pattern or rule to predict the number of jobs in May based on previous months. To improve, you should either provide a logical reasoning or state that the answer cannot be determined. Let's use this loss to backpropagate through the LLM call to see if it actually improves the answer. And here you can see, to do that, we call loss.backward. For those who are familiar with PyTorch, you would know that this is exactly how we sort of backpropagate and update weights in neural networks. So if we run this, you basically see that the answer becomes, I'm very bad at this, because by receiving the loss from the evaluation model, it has decided that, okay, yeah, I can't answer this. Let's take a step back and look at what exactly happened under the hood to prompt such behavior. And so this time I am also printing everything that comes out at each step. So the first thing we are printing is the loss that evaluation model told us. And the answer of 20 is not logical, etc. And then we have this thing called the gradient text. So the gradient text is basically the feedback that you're giving to your trainable variable, which in our case is the answer. The answer is what I'm going to train to improve it on the next round. So the gradient text the answer thing receives is that the answer 20 lacks logical support, and then it receives this sort of information that you have to acknowledge the uncertainty, you have to clarify the basis of the answer, and you have to follow the required format. And also, if you can't answer, you have to say I'm very bad at this. So by implementing these changes, the response will be more aligned with the objective of providing a concise and accurate answer to the question. And so, as you can see, the answer then changes after that optimization step to be, I'm very bad at this, which is what we wanted. It might be also interesting to see the prompts that were sent into the LLM for this to work. So to do that, I wrote a little script that prints out what's happening under the hood. So if you look at the log, so the first thing you're doing is the function forward. So you're basically doing a forward function call through the LLM. And this is happening when you're doing this initial answer equal to model of question, where you're passing the question through the forward pass of the model. Next, we are calling another forward function, but this time we are calling the evaluation framework. And if you look at the code back here, you'll see that loss equal to loss fn answer. So loss function is basically this text loss component that has this evaluation instruction. And also, it's important to note that for this example, I use the GPT-4o mini to be the evaluator, whereas the model which is actually going to output the answer to the question is GPT 3.5. Now, this is a very common theme that you're going to see in this tutorial, as well as the documentations and the notebooks provided by TextGrad, where the evaluation model is often a stronger model that is trying to train a weaker model to do its job better. So if you go back to the history once again, we have this LLM function forward, which is the loss function, and here you can see this is exactly the prompt that we gave it. So after that, what happens is that we are doing this backpropagate through LLM prompt. You will see something that we never actually wrote. We have never actually written this prompt. And the prompt says that here is an evaluation of the variable using a language model. And inside here, you will have everything that was inputted into the evaluation model. And here you have the LM output, which basically contains the loss output generated by the evaluation model. And here is the objective function, which is also hard-coded inside TextGrad, that asks it to give feedback and criticism to the variable so that it could be improved. And then we give the variable again, and then we ask, given the above history, describe how a concise and accurate answer could be found. And then again, the output of this backward propagation is going to give us all of the information that the answer 20 lacks logical support, and it has information like acknowledge uncertainty and all of that. And basically we are going to use that, as you saw here when I printed out the gradient text. It's basically the same thing here that is written over here that I found from the logs. If you go back to the neural network analogy, we have come up till here. We are generating feedbacks to update some variables in our computation graph. Now the next step is to actually do the update based on the given feedback. So I hope that sort of makes sense. So we had 4 steps. First, we calculated the forward pass of the model. And then here we calculated the loss. Then we do a loss.backward, which generates these feedbacks that we have, which we have printed over here. And the final thing we have to do is to actually update the answer or update the variable that we are trying to optimize, which we do by running optimizer.step. And remember, optimizer was set up earlier as this textual gradient descent thing, and we had passed in the answer, which again is the variable we're trying to optimize. So hopefully, all of that is starting to make some sense about how these connections are made. So if we go back to our text logs, so here you go, textual gradient descent prompt for update. We are basically giving the question and giving it the feedback that was generated, and then we are asking it to improve the variable, and we are asking the LLM to output the improved variable like that. And then we are again passing this prompt into the LLM. This entire prompt is getting inputted inside the LLM, and the output of this prompt, this optimizer.response, is basically the answer we get finally. So those many steps are happening under the hood while this optimization process is happening. Now hopefully that sort of does a bit of an icebreaker on what TextGrad is all about. And now we're gonna jump to our next example, which is example 2, aptly named. Also, please don't forget to hit the like button, subscribe to the channel, drop a comment below if you have any questions, because that helps out the channel. It makes me feel better. It makes you feel good. Let's go. I always put all the code, all of the slides, everything that goes into these videos on my Patreon page. So if you want access to anything that's produced in the channel, please consider signing up on my Patreon. That also supports the channel, helps us grow, and keeps us moving forward. And a big thank you to all of our Patreon supporters and YouTube channel members for this month. Thank you. You guys are magnificent. So here I'm trying to show that maybe sometimes you have two inputs that go into an LLM, and then out comes an output, and you want a single input to be optimized and the other input can stay the same. So we are going to go through an example like that. So as usual, we set up our main engine, which we're going to do the forward pass, and the backwards engine, which we're going to do to the loss calculation and the backpropagation steps. Oh, and also a quick little side note, if you have created an engine, you generate responses from it by using this engine.generate function, if it's useful. So here our goal is we are going to provide it this thing called 2 + 2 = 5. Okay, so and we want the model to correct this entire prompt. Because obviously the input sentence is wrong. The input sentence should be 2 + 2 = 4. So we are going to create a loss, and the system prompt for the loss is evaluate the correctness of the sentence. So if we run that, and then we create a variable, and here is very important, we are saying requires_grad = true. Every parameter in your LLM graph, if they have this requires_grad = true, then it's basically going to receive all of the backpropagation updates. If you have it as false, then it's not going to be using any of the backpropagation stuff. So for this one, we want to change this string to something else that makes more sense. So we're going to use this requires_grad as 2. And then we have this textual gradient descent, which we also used earlier. And then we again have this loss, which we're going to pass this string into this loss function. And then we're going to do l.backward and optimizer.step. So I'm going to let it run. Okay, so it is finished running. Okay, and now if you see the x.value, it's 2 + 2 = 4. Hooray, we made it. And obviously, if you want, you can also look at the gradient text like that. And here you see this thing like to improve the sentence in the context of the objective function, consider the following feedback. And then you have this entire thing called the primary ratio of the input sentence is its mathematical inaccuracy. That's true. It is mathematically inaccurate unless it's 1984. Now in the next example, we're going to try something a bit more weird, but I hope you get the essence of what this means. So here you saw that it says 2 plus 2 equal to 5, and obviously when we ask the LLM to correct this, it says 2 plus 2 equal to 4. Now what if we wanted the LLM to output 2 plus 3 equal 5? Because that's also a correct sentence, right? Let's see how we can do this. I have basically set up all of the variables separately. So you have an x, which is going to be a changeable operand, which is going to start as 1, and we're going to say that requires grad equal to true, and we're going to have a y that's going to be 2 and a z equal to 5, and then we're going to have this format string, which is basically going to be the statement. So the statement is going to look at statement colon 1 plus 2 equal 5, and this is the input we're going to send to our LLM. Notice that only x has the requires grad equal to true and everything else is false. So ideally we would want all the backpropagation steps to reach only x, and y and z are going to be fixed. Now let's see if that actually happens. Again, we write the loss system prompt, which is basically the same as we already did up here somewhere, here, right? The loss system prompt, which is basically going to say evaluate the correctness of the statement. But now we also have to generate the loss. To generate the loss, I'm using this thing called formatted LLM call. What is that? If you read the doc string a bit, it basically says that this class is responsible for handling the formatting of input before calling the LLM. Format string is this thing that I wrote out here. We basically needed to add this plus and equal thing inside the evaluation call for it to work. We have the fields, which are the dictionary that it's going to input when we actually call this, and we have the system prompt, which we wrote out here. We have specifically asked it to do not solve the answer, just provide the feedback, ensure that the equation is correct. And now we define this loss function, which is going to take in the x, the y, and the z, and it's going to call our formatted LLM call to do the deed. And then we have the optimizer, which is again the textual gradient descent optimizer. Let's see how this happens. So if you remember x, y, z, we sort of had initialized it over here. Let's just bring it down here so that we can see it more easily. The x is 1, y is 2, z is 5, and here we have requires grad is true for x. Let's see if we run this, what happens. Oh, I didn't run everything above it, so nothing's gonna happen. Okay, now something's gonna happen. Okay, something is happening. All right, so now we have done this, right? And as you can see that x.value is now 3. So here you can see that if you look at the loss, it does indeed figure out the statement is incorrect. The correct sum is 1 plus 2 equal to 3, not 5. Notice that the loss function itself did not output anything about the variable x. The loss function is common for all the variables that you're trying to optimize. So obviously it has no information specifically about x. But if you look at x.gradient text, you will see that it does indeed nudge it to say, for example, changing 1 to 3 would create the equation 3 plus 2 equal to 5. And for the gradient text, it says that discuss how changing 1 to a different value would lead to a correct statement. For example, changing 1 to 2 or 3 could create new statements, such as 2 plus 2 equal 5, 3 plus 2 equal 5. Okay, so that's the second example. Let's jump into the third example. In the third example, we are going to be inputting a code, and we're going to ask the LLM to improve it. And now here we have, again, set the engine to 3.5 turbo. Now obviously it's a very old model, but it will do for this demonstration. So here I have a function that lets you input a code like a string and return us the Python function. I'll quickly show how this works. So here we had some code that's in a string format, and then it converted it into a function, and here we are able to run that function. And so if you come back here, here I have created a very basic search code. I have said that you have to search for a value in a sorted list. I have given it a problem statement, said that I will give it an input sorted array, and the output would be the integer, which is the index of the number if present. And here I've given it an initial solution. Now notice that here I'm doing like a linear search where I'm scanning the entire array, then basically just returning a true or false. The problem statement obviously asked us to return the index of the array. So it's not only wrong in the output it returns, it's also wrong because if it's a sorted array, you could just do a binary search instead of a linear search, and that's going to be log n time. And so obviously if we run this function through a list of our arrays, we will see that it is indeed showing the runtime to be order n. As you can see, it's this linear It's kind of a straight line that shows that as you're increasing the size of your array, the time taken to run these functions is also increasing linearly. Now let's see how we can improve the code. So here I have said that here is the engine, which is the GPT-4o mini, and I'm going to input the code, which does require the gradients, and the problem, which is the problem statement. It does not require gradient because it's the coding problem. And I define the loss prompt, and then we again use that formatted LLM call function, which formats the input like this, the problem and the current code. And then we run the loss function by passing in the problem in the code. And you can immediately see it identifies the problems. It says that the return values are true and false, but it should be index or -1. It also says that the efficiency is a linear search. Since the array is sorted, we can use binary search. And they have also said some things about the parameter naming and things like that, and also at type hinting. And so if we did the loss.backward and looked at the code.gradients, then you're going to see everything that the loss said, it converted it into a gradient based text. And then we do our optimizer.step, and now if you look at the updated code, it is indeed working on a binary search. It's calculating the middle, and then depending on whether it's lower or higher, it's jumping to a lower or higher. It's basically like dividing the array in half at each iteration. And if we did the same sort of a complexity analysis, you can also see this orange line, which is basically the time it takes to run the new code, is much lower than the blue line, which operated in linear time, and the orange one is O log n. That's another example where you see that you had some code and you have some problem statement, and you use the LLM to evaluate your code against the problem statement, and then do this backpropagation gradient update thing to update the code. We're going to jump to the next example, which is going to be a math example. Now here I've asked it to find the critical point of this function fx equal to 6 of x squared minus log x minus 5x squared plus 11x. It's just completely random. But now obviously the correct way to do this will be to take the first order derivative of this fx function and then solve for x. So taking this derivative will return us this particular equation, and then we can apply the formula to get our 2x1 and x2. And because one of the solutions is negative, we have to also eradicate that because we already considered a log x for that term. So the answer is actually just 1/2. And here we have given it an initial solution which states the problem, but here it does a bunch of random mistakes. Like here I have randomly change this pluses to minuses. Here it is to be 2x squared plus 11x. So here it is to be 2x squared plus 11x minus 6, and I've done random like calculation and arrived as a 17x squared and plus 6. And here also I've done a bunch of random things to basically arrive at some random solutions. And then here I have put this initial solution of this step-by-step thing, which you can, by the way, also ask an LLM to generate, and then basically use that generation to improve on it. But here I've just started with an initial solution that is flawed, and I have inputted it as a variable, and I've said that it requires grade equal to true, and I've defined the loss prompt as usual, and I've defined this text loss and the optimizer again as usual. And then I calculate the loss again, and we receive some feedback about things, and it basically says that okay, there are a lot of wrong answers. The calculation of the discriminant is incorrect. Then we do this loss.backward optimizer.step to update the variables, and now we have the solution.value. And if you look at the solution.value, it basically generates two solutions. It says fraction of 1/2 is a solution and x2 is -6. So obviously that's wrong. Both solutions are real number, with x1 being positive, x2 being negative. That's obviously wrong. So we can run the loss function again on this new solution, and now it does figure out that the solution derived from the quadratic formula are correct, but the interpretation of x2 equal to -6 is problematic since the original function involves log x. So it figures out in the loss function in the second time around that yeah, indeed it's incorrect. And now if we run the loss backward and optimizer.step again, and then check the solution.value again, we see that finally we have the two solutions, but x2 is equal to -6 is an invalid solution, and it says the only valid solution is 1/2. So again, able to generate a response that's more accurate, that's more concise by using this idea of a gradient. And obviously you can also print this out in LaTeX to see how that looks in a pretty format, and that's how it looks. Enjoy. So we're going to jump to our last example, example 5. So far we have tried to optimize the input query. We have tried to optimize the solution outputted by the LLM. But this time we are going to optimize the prompt, the system prompt that we sent into the LLM to do its job. Specifically, I have collected a data set which contains question and answers. These are questions from football scenarios. If you have seen my tutorial on DSPy, you'd probably recognize these data set. It's basically a data set I collected from Claude, where I have some inputs which contains some situation in a football game, and the answer is the referee decision. So we have a data set and we want to train or find a prompt that when we input the question and that prompt, it gives us the answer correctly. Let's see how we can do that using TextGrad. Here I have written a system prompt which basically says you are a football analyst, and I'll give you a situation in football and you must choose from the following. So I've given the 6 or 7 categories that are allowed to be chosen from, and I also wrote that your output should exactly match the given values, just the category string. Once again, to do the loss, we are going to use the LLM formatted call, where we are going to give this format string, which we're going to pass the LLM prompt, the query, the prediction from the model, the ground truth, which is the target we want to set, and the evaluation, which is basically going to say if the model was correct or not. And here we have the usual stuff that we have had before, and here we have a short example where we are just inputting a single question and seeing how the pipeline works. So here we have the question, which is basically derived from that data set. We have the target, which is again the answer like this from the data frame. Then we pass that into the model. Now you'd notice that this model was initialized right here. You initialize it as a black box LLM object where you pass in the LLM, which is GPT 3.5 Turbo, and you have the system prompt, which I just talked about. But I did not mention last time that it has this requires grad equals to true. So we want to update this thing now. We are going to update the prompt now. If you look at the query and the target, we're not updating any of them. We are not trying to update the target or the question. We are trying to update the prompt. We want a good prompt that works for a lot of cases. And so here you see that the input was tackled from behind. The target was yellow card. The model predicted red card. Now, obviously, it's not wrong, but you know that's the data set that I have. And you see the loss that the prediction does not match the ground truth label. The tackle from behind typically warrants a yellow card. So that's not always true, but it's all right. Now we're going to run our optimizer.step function. So that's going to run for a bit. And then finally, if you ran that, you're going to see that it indeed says a yellow card now. So up till now, everything is fine. But let's look at the system prompt that was generated here. System prompt. So here you have the updated system prompt. Wow, that's a long prompt. Now notice that when we initially made the system prompt, it was quite small. It was just this, just output one of this. But here now you see that it's a long prompt and it has a lot of information. It has a lot of information. Ensure that your choice reflects the exact terminology, like reinforce the no commentary rule, while the prompt states that the output must be a single word or phrase, reiterating that, okay, there's a lot of things that it tells it, and then it finally outputs yellow card. Good. Now, obviously, we want the system prompt to be tuned by looking at multiple examples and not just one. Now here we only trained it on a single example. We just gave it one single example and asked it to optimize the prompt. Obviously, that's not a good idea. Ideally, even in training a neural network, we would train a batch of data together and then update the weights by considering the gradients obtained from multiple data points inside the batch. That's what we're going to do next. We're basically going to take this data frame we have. We are going to pass 5 or 10 questions, get their answers, do the backpropagation for all of those 10 questions, accumulate all of those 10 questions together, and then do a gradient update so that the new prompt has a lot of information from different examples in our dataset, not just one. To do that, I have written this function called Finetune prompt, which basically takes in a data frame, it loops over the data frame, extracts the questions as well as the target, creates the question variable, which again requires grad is false, target requires grad is false, then it generates the prediction, and then it creates this evaluation string which says if the prediction is correct or incorrect depending on the values of the prediction and the target. And then we pass that into our loss function where we give it the system prompt, the query, the prediction, the ground truth, and the evaluation, and we append this inside the loss.append thing. Notice we don't call loss.backward as we had been doing so far. We are appending it inside a list. And then when that list has at least 10 items, we are going to do this tg.something, which concats the values of different gradients together to form a combined feedback that we are going to give it to the LLM. So here we are doing that, and then here we are doing the total loss.backward, which is running the backward loss step, and then updating the weights. And if we print the evaluation scores, we will see that just on 60 examples, the prompt was improved from 0.5 to 0.75. So it basically says 0.6, but this is after the first iteration was already done. If I ran this on the original prompt that I had sent, it was actually 0.5. So, and if you print out the system prompt, you're basically going to see, wow, there's a lot of things. You are an expert football analyst with a deep understanding of the rules and nuances of the game. I'll give you a situation in football. Okay, that's a long string which I'm not going to read, but yeah, it provides a lot of things, man. It says, it gives the strategies it should implement to answer the questions, and yeah, and then it gets these kind of accuracy. So again, so those are 5 examples that I wanted to share about TextGrad. The first one was a simple one where we just showed how a solution could be improved upon to prevent hallucination. The second one was an extension of the idea where we were optimizing the input instead of the solution. In the third one, we saw how we can use to improve code. The fourth one was to solve a simple equation. The fifth one was to generate prompts from a dataset. If you go to the TextGrad documentation page, they have a bunch of these collab notebooks that you can also try out. And hopefully, after watching this video, you're going to have some understanding of how it all works and how it all integrates with each other. That's been my time, guys. Hope you enjoyed this video. I hope you learned something new. I'll see you next time. Bye.